Good morning. Thanks for joining me today. I'm glad you're here for the first talk. I know it's a little early still. I work at a tiny company called Pingboard. We're just a little startup. I'm the data analyst. I am the data team. And so mostly I count things. I count things to see how people are using the product and to see how they're getting to us and how the business is running. But we actually care about the future as well. So we want to know how all of our objective key results are doing over time. Are we going to meet our goals? And we want to see how people who are adding new org charts, whether they're going to keep building them at a certain rate, and what our predictions are going to be. So we do actually want to get into forecasting. So to some extent, this presentation is me figuring out what kind of forecasting I can do at work. So thanks for giving me the opportunity to do that. I'm going to talk about a few different techniques. Everything is going to be done in a Jupyter notebook with Python and pandas. And don't worry about the code. You don't need to find it and follow it. It'll all be downloadable afterwards. We're going to look at ordinary least squares, polynomial fit. We're going to spend the chunk of our time on autoregressive integrated moving average models. They're called ARIMA models. They're from economics. And then we'll take a step back, and we're just going to let Facebook do it for us. There's a nice library from Facebook that just handles all forecasting. And then we have a few minutes to talk about model evaluation at the end. I found this data set via Google Dataset search, which I didn't know about until my coworker told me about it while I was prepping for this talk, so I thought I'd share it with you. It ends up being on Kaggle. It's a really cool data set. It has it's about bike rental data over time. So it has the casual rentals, the regular rentals. It has all sorts of information about the humidity and the temperature and the wind speed, and we're not using any of that today. But if you ever wanted to play with it, it's out there and you can. We're using just total rentals over time. So this is what our data looks like. It's not the easiest, prettiest data set to forecast, and that's what's going to make this fun. We're going to try and forecast out a little ways from here and see how well each of our methods does in trying to go forward from this data set. That's why. So we'll start with ordinary least squares, which maybe some of you are familiar with, or you may know it as linear regression. Ordinary least squares has a lot of great properties for any time you're trying to fit X explains Y. But it does make a lot of assumptions about the data that don't always hold true, and especially don't hold true for time series data. One of the assumptions is that there's no autocorrelation in the errors. The errors are uncorrelated with each other. But our time series data, it has the thing, yesterday looks a lot like the day before it. They're usually pretty close to each other in time. It doesn't just hop all over the place. So it's not gonna have that property, and so it's not ordinary least squares is not gonna be the perfect method for this, but it still can get us going pretty good. We just use a built-in SciPy function to get the linear regression. It's just the line of best fit, y equals mx plus b, as you may remember from elementary school. And then all we have to do is add the slope and the intercept to get our forecast. So our orange line is our fit in the actual data, and our green line is our forecast out 60 days. So this is the error minimizing line for this data set. But our data set isn't linear, so maybe we should fit it with something else. Maybe we should use some curves. This has less statistical rigor around it, but it still is something we can do, especially if we're just trying to make a model that looks like our data in the short term. And again, this is something built right into the scientific programming stuff. So NumPy has a polynomial fit. All you have to tell it, let's see if I can do this, is the x data, the y data, and the order of the polynomial. And it just fits it. And then we have our forecast out. And it fits the curves a little bit better. But how did I choose a polynomial of order 3? Well, I tried some other polynomials, and they didn't all make a lot of sense. The polynomial of 5 fits the data in our current data set really nicely, But when we try and forecast out 60 days, it predicts minus 7,000 bike rentals, which is not going to help out. It's not going to be a very realistic data set. So be especially careful with polynomials when you're trying to figure out, when you're trying to extrapolate forward and forecast. Even though you can get this beautiful fit of the data that you have up until that point. All right, here's where I'm going to nerd out on you. Hang in tight, it's okay if you don't get all of this. This is almost an entire semester of economic forecasting. Autoregressive integrated moving average models come from economics. I've had to take this course a couple of times, so it's something that I'm a little familiar with, so we can talk afterwards if I fail to explain it. And it's just how the economists think about time series data. And we're going to figure out how, if you get through this and have some idea where the parameters come from and how it's used, then you're doing great. And you can always look at the Python notebook and figure out how to do it yourself afterwards. So the first thing you have to do with data for an ARIMA model is you have to make it stationary, which is kind of ridiculous. You have to have a model with a constant mean. You have to have data with a constant mean in order to predict the trend. What? But that's indeed how we do it with time series data. We do something kind of really simple. If the data is not already that way, we call it differencing. So instead of looking at yesterday, we look at the difference between yesterday and the day before. And this is so common that it's a built-in pandas function. So it's just dot difference, and it'll do it. And this is what our data looks like when we difference it. So we get this nice mean zero thing going on. And just the format of the model requires this. If we don't do this, then the matrix that we try and invert when we try and solve the model just doesn't invert. So we have to get our data to be stationary. And the number of times that we difference it is called the order of integration, and that's the integrated part of the ARIMA. There's all those other letters too. So the autoregressive part is the function where the future is a function of past values, where you say that yesterday is like the day before, or is like the day before that, or some function of those days. That seems pretty straightforward, but a little different is the notion of the moving average. So we have the stationary data that has a constant mean. And what the moving average is kind of saying, how much does a shock to the system, does an error at a certain time point, how long does it stay with the system, and how much does it propagate through the system? So we're saying, how long do errors continue to affect what's going on in your future values? And now we have all the pieces to put together the parameters for the ARIMA model. So y is going to be a function of how many past values of y. We have p lags for autoregression. We have that order of integration, the number of times we difference the data to get it to be stationary. And then we have how many past error terms we want to use for the moving average piece. How do we decide what p and q should be? Well, we actually have some charts we can look at that help us out with this. I know this is a lot of code. I'm sorry. A lot on one slide. The autocorrelation function is just the correlation of y with past values of y. So you're just saying, what's the correlation of yesterday with 3 days before that, or the 5 days before that? And it's right here, this thing. And for some reason, we always do we always do the 0 with 1, just so we can be really sure that yesterday correlated 100% with yesterday. So make sure we understand correlation. We're in good shape there. And then we have this -2 correlation for yesterday with the day before. And that's through the length of the whole data set. Then the partial autocorrelation function is a little bit funkier. Instead of just taking the correlation with the past values, it makes a quick little OLS fit of however many past values back you're going, and then takes the correlation with that and says, how much is this error still providing information into the system? And the rule of thumb for these is that usually one of them will have significant lags and the other one will drop off pretty quickly. And if you have significant lags in the PACF, in this case we have 5, 1, 2, 3, 4, 5, That's going to be the order of your autoregression function. But if we had them up here, then it would be the order of our moving average function. So we have the quickly decaying ACF and 5 lags in the PACF. So we're going to try and do an AR5 model. And I can do what order. And so all we have to do is tell ARIMA, it's just built right into stat models, that we're doing a 5-1, because remember we had the difference at once. And it spits it all out, does the forecast. I do want to take a second. I redacted most of the fit summary because this was a really busy slide. But I do want to take a second to look at the coefficients. So we fit 5 coefficients, 1 for each lag. And if you're familiar with regression, or if you're not, this p-value is for the hypothesis test that this coefficient is really 0. So we're saying that the probability that the first lag really contributes nothing to the model is so low that it looks like 0 to us. So we feel really confident from the fit of the data as well as from our heuristics that these 5 lags are all contributing to the model. So why is it an ARIMA instead of an AR or an MA? It's because you can actually combine AR and MA models. It turns out because of math, an AR model can be approximated by an MA model, and an MA model can be approximated by an AR model. But we have this simple rule that simpler models are better. We want to have a model with the fewest things to estimate that still does the best job we can of fitting the data. So by combining the AR and the MA functions, sometimes we can get something a little bit smaller that still does a really good job of actually explaining the data. So how do we really choose models if we're going to combine these things? Because we usually see either lags in the PACF or the ACF when we're looking at the charts. We use information criteria to use this. So information criteria is from information theory. And it says there is so much information in your data set that your model is going to only approximate that much information. And so you want to choose a model that has the least amount of information loss. But we're also going to have some, the criteria also have built in some account for how complex the model is. So back to simpler models are better. So we want to make sure that we don't just say that we can fit the data perfectly by having the most complex model in the world, but then we're just overfitting. So we let the computer choose several models, and then it's going to use one of these information criteria, the Akaike information criteria, to choose the best one. And again, it's built right into stat models. You'll notice it's an ARMA order select. So we have to do it against the difference data. It doesn't know about ARIMA. It doesn't know about integrating data for itself. And so all you have to do is pass it the Y data and ignore it spitting out a bunch of SciPy future warning errors. And then it's going to tell us that the most efficient model that it thinks we can do is an order of 1-1. So an AR1, MA1. So let's go ahead and fit that. And again, all we have to do is pass the order to the ARIMA function, and it goes right away. And we fit only two coefficients at plus the constant this time. So we have a simpler model. And we forecast out, and we still have all these nice properties where the ARIMA model is aware of where the data left off, and so it forecasts out from that point. So how much did we gain? How much information did we get more of by changing models? Our AIC only went down a little bit, but we also went from 6 parameters to 3. So in this case, it's probably not a huge difference in how good a model we got, but it's still something that we still have one that's more efficient that we know about that now we can use. Okay, I'm sorry for rambling on about economics for that long. Thank you for sticking with me. Now we're going to do easy stuff. Facebook released this really amazing library. It's available for both R and Python. It takes care of seasonality, which we haven't even touched on yet, but there's a whole nother lecture on how to get that into ARIMA. So it's just very straightforward to use. So let's try it. The only little caveat is it's very particular about its data set. You have to give it date stamps and a Y function, and it has to be named exactly that. And then all you have to do is say, Prophet, come help me, fit my data set. And it fits it, and we forecast out our usual 60 periods, and we get this. The black dots are the actual raw data. The blue line is the fit, and then the pale blue is the error bars around the fit. And this part here is our actual forecast forward. And you'll notice that it continues, even unlike the ARIMA, it continues to have the squiggliness because of the seasonality. And it will even spit out what the pieces are of the model that it built. So it tells us that, yes, there's a trend, which I think we've believed in since the OLS example. We believe there's a trend. And then there's day of week seasonality. More people ride bikes on Friday than ride bikes on Monday. Okay. And there's day of year seasonality. More people ride bikes in July than ride bikes in January. Sounds reasonable. But that's not all. Prophet has built-in country holidays for a bunch of different countries, including the US, and it's a one-line change to add them into the model and ask for them. So all you have to do is say add country holidays and pass a country name. And then you can refit our model. Again, it's just the same 3 lines of code, complete with the plot. And you'll see that there's some differences. Now we have, our fit has a bunch of these jagged spikes that are trying to follow the data a little bit more. And we can see them again in the components. So I think this is Thanksgiving and Christmas. I think this is 4th of July. So now you have all these models that you can build, at least once you get the Jupyter Notebook and start playing with it. So how do you decide which model you want to use and how good it's doing and decide about these things? So first we're going to split the data up into 2 pieces. We've just been forecasting off the side. We've just been going, all right, we're going to go 60 days into the future. But we don't know what the future looks like yet. So we're going to have to go back into the past so we can pretend that we don't know what the future looks like and have some pretend values. So we're going to take this part, the blue part, and we're going to use that to train all our models again. And then we're going to use them, we're going to test them against the orange part and see how good they do. And how do we decide what's good? We want to know who has the least root mean square error. And this is all the code it takes to refit our whole set of models. We fit our ordinary least squares, and we had a root mean square error of 3,200. Okay, that's a number. We don't have anything to compare it against yet. That's okay. We fit our polynomial, and we fit the 3 because the 5 didn't seem like a good idea. And our root mean square error actually goes up to 4,800. And that's because we lose this downward piece for the polynomial to fit against. And so when it fits the polynomial, it just happily curves upward because that's the direction it's been going. And so it's going upward and more than linear. And so it does a less good job of fitting than the OLS. So maybe the polynomial is not the best for forecasting, even though it does so nicely in the data that we already have. And then we fit our ARIMA model. We go ahead and fit the 111 that we know is most efficient. And our root mean square error drops all the way down to 2,300. So we're finally making some progress. We're getting some data models that are doing a little bit better. And Prophet, of course, complete with holidays, does a little bit better. It gets all the way under 2,000. And then you still have to decide which of these you want to use and for what's going on. And so there's some amount of your appetite for explainability that matters here. If I'm just trying to do something that for the year forward and I want to talk about how well we're reaching our goal, I might actually still use OLS because I want to report that trend back. I want to have some information about that trend line that I can share. But if I want to talk about how I got the data and where it came from and explain what all of my parameters mean, maybe I need to use an ARIMA model So I'm not going too far out into crazy land. But if I just want to fit it and I expect it to go really well and I don't have to explain it to anybody, then Profit's right there for you, and it's very easy to use. So hopefully that gets you started. Thanks for listening. All of the slides in the Jupyter Notebook are on my GitHub. Enjoy forecasting.